Okay, welcome everyone. I believe this is the 107th meeting. If it's the 106th or the 108th, I apologize, of this seminar, New Directions in Group Theory and Triangulated Categories. Our speaker today is Vladimir Sosnilo from University of Regensburg, and he'll be talking to us today about resolutions of C categories.
Okay. Yeah, so let me start. I prepared a 1-hour talk, but as it often happens, I might go over time. But I do need to introduce some things before introducing the subject in the title of the talk. So I'll have to start from something that is sort of irrelevant for the talk at the moment. Please bear with me nevertheless. So I'm going to start with bounded weight structures and weight structures in general. So yeah, let me quickly give you a definition. So let's say C is a stable infinity category. A lot of the things that I'm talking about work in the triangulated setting as well, but they're just much easier to formulate in the infinity categorical setting. So if you have questions about this, ask me at any point as well. And so weight structure in C consists of is a pair of subcategories
Hi, I'm just curious. Are you writing with your mouse?
I'm writing with a tablet.
Okay.
Why? Is it completely unreadable?
No. It is perfectly fine. I was just curious.
Okay. Yes, satisfying a few axioms. So the first axiom is that they're closed under correspondingly negative and positive suspensions. Second axiom is there is this orthogonality condition that if you take any object in one of these categories and an object from the other one, then the mapping, the mapping set from y to sigma x is going to be 0. And the third axiom is that for any object in C, there exists a decomposition such that this is correspondingly co-connective, as I like to call those, and this is connected. Yes, so this is a general definition. You can make sense of morphisms. By this, I mean functors of weighted functors of categories that preserve the weight structure. Preserving the weight structure. You can also make sense of some reasonable conditions like boundedness, which you commonly encounter in the very surfacely similar theory of T structures. So you can also say that the weight structure is bounded. If and only if any x in C, or let me write it this way, that C is the union of minus n, oh, sorry. n intersect minus n for an integer. You can also make sense of the heart, again, similar to the notion of it, similar to T structures.
Bova, can you just say what's the difference between a weighted structure and T structure? What's the axiom missing?
Yeah, sure. So the main axiom, I mean, I guess, yeah. So the first axiom is the same in both cases. You have the class of connective and co-connective objects, they're closed under respective shifts. But then the second and the third axiom are dualized. So instead of this orthogonality, you have exactly the opposite orthogonality, and the fiber sequence, you also have the opposite. So in a T structure, here you have a connective cover, so it's going to be connective. And here you have the co-connective part, the truncation. So this is the main difference.
Excuse me,
right.
Maybe in your second axiom, you need to swap y and x.
Yes, I do need to swap y and x. Thank you, David. Yeah. Right, so I can make sense of the heart of the wave structure. And, this is the intersection of the connective and co-connective objects. Right. So far, this is, yeah, this is all the formal information I want to tell you about wave structures, maybe at least at this point. But I want to give you one intuitive explanation about why we need this theory altogether. So at least from the point of view of noncommutative motives, we want to think about categories as some generalization of the notion of a scheme. So typically, if you have a scheme, then you can assign to it the category of perfect complexes over itself. And this gives me a very nice stable infinity category. Which under nice conditions also satisfies this. So in the world of stable infinity categories, there is a notion of a smooth category, there's a notion of a proper category, and this correspondence respects this notion. So a smooth and proper variety over a field, say, it gives me a smooth and proper category. And in general, well, I wouldn't say all of the results in algebraic geometry could be reformulated, could have some mirror image in some image in this categorical level, but a lot of what you want, especially a lot of homological algebra, a lot of statements about homology theory of algebraic varieties, they can nicely be translated into this categorical language. And sometimes you can even go back by proving some very general statement about categories and specializing it to the case of schemes to some very non-trivial things. So in particular, yeah, as I said, this works very nice for some homology theories, and some examples where it works very nicely is the cohomology theories coming from the level of from the K-theoretic level. So we have the K-theory functor. We have all this kind of periodic version of the theorem complex and theorem cohomology. So we have Hochschild homology, we have periodic Hochschild homology, and things like that. We have this cyclotomic trace class map from K-theory to one of these versions. So I mean, it really has some. So this categorical level really does contain some geometric information which can be useful in practice. The meeting is being transcribed. I don't know what this means. But I got to say that some notions, for some notions, this correspondence from schemes to categories, it does lose information. And for instance, if we start from, if we start from two different rings, say R and R prime, well, or maybe, okay, maybe let me start from two schemes, X and X prime. And to them, I associate these categories of perfect complexes, perf X and perf X prime. And it might happen that these categories are equivalent, even though the original schemes were not equivalent. This can be found even in some simple examples with abelian varieties. And this is one problem, and maybe another problem that I want to mention is that some geometric notions are very hard to formulate on this categorical setting. So one original motivation for bringing weight structures into this context for me many years ago was the theorem of Dundas-Goodwillie-McCarthy, which tells that if you have a map of schemes, X to X prime, which is a nilpotent extension. So this is a closed immersion. And the ideal defining this closed immersion is nilpotent. Then you want to understand what properties does the pullback functor have. And in particular, you want to say, you want to define a class of functors that you want to call nilpotent extensions so that you can formulate this theorem of Dundas-Goodwillie-McCarthy, which tells you that under nilpotent thickenings, the fiber of this cyclotomic trace is invariant. So so we want some kind of categorical nilpotent extensions. And the thing is, well, under this non-commutative interpretation, you can think of weighted categories as, so the notion of a nilpotent extension, as many notions in algebraic geometry, is a local notion. So this is something that you first define on affine schemes, and then you globalize to arbitrary schemes. And this suggests that you need some notion of an affine non-commutative scheme. And the suggestion is, this is exactly what weight structures are. So if you start from schemes, inside here you have affine schemes. So here you have this functor that gives you a stable infinity category. But the idea is, if you start from an affine scheme, the stable infinity category needs some extra structure, which is exactly the weight structure, exactly bounded weight structure. So cat st bounded weighted. Right. And yeah, so this picture turned out to be useful because you could actually prove a lot of results of this kind about nilpotent extensions, about some pro-excision kind of statements, or some kind of descent statement for weighted categories. And then you globalize, so then you can go back to schemes or algebraic stacks, if you like, or some other kind of geometric object, and get some result for them. But the never-ending caveat here is that you always have to, if you were to prove something about arbitrary schemes using this approach, you would have to first prove it for schemes, for affine schemes, and then get a result by descent for arbitrary schemes. So although this gives you some interesting structure, which is very helpful and covers a lot of examples, this is not enough for our purposes because we actually want to work with schemes. We don't want to work with affine schemes. And the idea is to sort of globalize this notion of a bounded weight structure in such a way that perfect complexes over arbitrary schemes would have this structure. So yeah, this is sort of the motivation and the first part of my talk. Right. Maybe let me not finish this part of the talk. I just want to say one more comment about this, is that the reason you could prove this kind of results about Dundas-Goodwillie-McCarthy theorem and things like that about weighted categories is because of the following theorem. That if you have, so you have the category of bounded weighted stable infinity categories, and you have this functor of taking the heart of the weight structure, and this goes back to this gives you an additive, at least an additive infinity category. And the claim is, at least if you restrict this functor to idempotent complete categories, this is an equivalence. So equivalence. I don't want to be super precise, but let me say up to taking idempotent subcategories. Of idempotent objects, idempotent complete objects. And so because of this, you can essentially think of weighted infinity categories, so stable infinity categories with a weight structure, as an additive infinity category. And an additive category is nothing but a ring with many objects. So it's like if you have an additive category generated by one object, this is essentially, this is the category of perfect complex, this is a category of free modules over connective ring spectrum. And if you have many objects, then this is just, I don't know, up to some filtered colimit, up to taking many objects, this is a ring spectrum. So yeah, slogan here is that can reduce all theory to additive categories. Theory to additive categories and connective ring spectra. So in particular, you can also define things like what I told you before. So you can make a definition of an nilpotent extension of additive categories, for example. So you have A to B, additive functor. Between additive categories. And then we say, so let me make a few definitions. We say that F is K connective if any object of B is a retract of F of something, and the map on mapping spaces is K connective. And for any xy in A, map xy to map fx fy is K connective. And the second definition that you can make is that of an nilpotent extension. So we can say that F is a nilpotent extension if F is zero connective, and for any composable morphisms, let me use a different letter for morphisms, sorry. So we have x0, g1, x1, xn, gn. And if we know that f of gi is 0, so okay, there exists an integer, there exists n, such that if we have a composable sequence such that each of the morphisms becomes 0, then the composite has to be 0. Okay, so yeah, this is pretty straightforward. You don't need to think too much about this definition. And this allows you to generalize this theory from classical connective ring spectra about nilpotent extensions to weighted categories. And in the end, you get this theorem, Dundas-Goodwillie-McCarthy, which tells you that for any A to B weight exact functor which induces a nilpotent extension in the heart, we have that the following diagram is pullback. So we have K theory of A, going to K theory of B. And here we go to TC of A and TC of B. And the following diagram is Cartesian. In particular, the fibers are isomorphic. Okay, now I can finally go to the second part. And let me know if there are questions.
Sorry, do you have a text where we can
It's
in more detail?
It's getting prepared, yes. Well, I mean, so far I've only talked about things that are already written. I don't know, for example, in the paper about nilpotent extensions. But what I'm going to talk now is not out yet. It will be hopefully out in a month or so.
Okay, thank you.
Okay, so the idea now is the following. Although you don't get a bounded weight structure, so on perfect complexes, so maybe I should have given you an example first. So how does it actually work? How does this structure that I mentioned work? So assume you have R, a connective ring spectrum. Then I can define perf R greater or equal than 0 to be the class of connective perfect complexes. So I mean, a perfect module over R, I mean, it's in particular spectrum with an action of R, and there's a spectrum, it's connective. This is what it means. And perf R less or equal than 0, well, it doesn't have such a familiar description, but nevertheless, you can describe it as the closure of the class of the set consisting of the object R, the free module over itself, and you close it under arbitrary finite limits and extensions and retracts. So in particular, it contains all the loops of R and all the direct sums. And then the hard, so hard in this case, is the category of free modules over R. So, oh, sorry, projective modules over R. So it consists of things that are retracts of a free R module. And in particular, because R is connective, you can actually see, so this orthogonality condition that was in the definition, it tells you that if you take any two objects in the hard, then the mapping spectrum between them has to be connective. And in this case, you can see it because the mapping spectrum between any finite free modules over R is going to be—
so finitely generated projectives.
Well, finitely generated projectives, yes. Yeah, so yeah, in particular, you can see that the mapping spectra are going to be connective as well. Yeah, so if you were to try to globalize this on perfect complexes over a scheme, you don't have this. So you know that if you were to take so finitely generated projective modules, globally they correspond to vector bundles. And if we look at vector bundles inside, I don't know, maybe I'll just write flat, inside perf of X, then this does not satisfy this. So for instance, you can find two vector bundles such that there are non-trivial X groups. So could be non-zero. So in particular, this couldn't be a nice example. But nevertheless, we always have the so-called compactly generated weight structure thanks to the theorem of Mikhail. So let's say that we have C, presentable stable infinity category. And we have any set of compact objects. So then there always exists a weight structure that has the following form. So we have C less or equal than 0 being the closure of S under limits, not necessarily finite extensions, retracts, maybe let me say direct sums, yeah. And in this case, the positive part can be described as the class of those objects such that are orthogonal to the negative part.
I would rather say that the author of this theorem is David Pogstella.
Okay, yeah, that's a good comment. Yeah. Anyway, what this means is that we can have an unbounded weight structure on the category of all quasi-coherent complexes over X. So let me maybe use this notation, DQC of X does admit a compactly generated weight structure. So yeah, a weight structure that satisfies these assumptions that satisfies the assumptions of the theorem is called compactly generated. But this is not too useful because, I mean, well, a priori, this is not too useful because we cannot control, like we're really interested in studying the small category of compact objects with this category. And now we're just saying that, okay, if we complete it, we get some structure that maybe does something, but it's not really clear what it does. And the idea here is that you can add some additional assumptions such that this big weight structure on this incompletion of the perfect complexes still remembers a lot about, still somehow doesn't go much beyond the level of compact objects. Well, let me be more precise. So definition. C, small stable infinity category. Now we say that okay, let me consider two conditions. So condition one is okay, not everything. So we have a compactly assume that ind of C has a compactly generated weight structure. So now we can consider two conditions. So the first condition is that if we look at the Ionad embedding of C into ind of C, that this embedding lives inside bounded objects. So this is by definition the union of in C less or equal than, well, let me make some slight abuse of notation. So there exists, and the second condition is that for any x which is weight positive, there exists a filter diagram in C such that the co-limit of xi is x, so filter diagram. And for any I in the diagram, there exists a map In such that the induced map xi to xn factors through an object of weight minus k for some k. Oh, sorry. So there exists k such that this is satisfied. Okay, so this might be very, this might seem a little technical, but let me give you let me give you a reinterpretation of these conditions. Okay. Can you come a bit late? I'm giving the talk right now.
Yeah, I just write down what I want to say in the past.
Okay. Okay, so yeah, remark. So these conditions might look a bit might look a bit huge, but let me just try to emphasize.
Sorry, what does it mean? Exist I to n?
So yeah, I mean, so we have a co-limit over a filter over some filtered category, and there exists for any object in I, there exists a morphism I to n in this filtered category such that this is satisfied. So, okay, sorry about that. So to 2 is equivalent to the following. So under the first condition, we have the following picture. So we have C embedded into the bounded objects inside int of C. And we might consider the Verdier quotient of this embedding. I mean, up to some set theoretical issues that this is not a small category, but in fact, you can avoid them. You can take the Verdier quotient. And the idea is that, okay, we have our category C that we want to study, and we know how to study bounded weighted categories. And okay, the condition 1 tells you that you can embed C into a bounded weighted category. But somehow next you need to induct. So you also want that this category on the right is going to be a bounded weighted. And maybe, or not bounded weighted, but it has the same structure as C does. And this is more or less exactly what is the second condition tells you. So if you denote this by Yoneda, and this is, so the right adjoint that exists on the level of incompletion by Yoneda upper star, then what this condition is telling you is that the functor, the composite Yoneda composed with Yoneda upper star from int of C bounded to itself sends connective objects, sends weight connective objects to weight or to objects that are minus K connective. And in particular, from this condition, from this reinterpretation, you can see that in case 1 and 2 are satisfied, we know we can figure out that for this quotient category, 1 and 2 will be satisfied, but 2 will be satisfied for greater K. So let me formulate sort of a lemma. Assume 1 and 2, and 2 technically has an integer in there hidden, and so I want to say then int of C bounded mod C satisfies one and 2 K minus 1. Okay, and so to finish the definition, I want to say that C is a pre-C category if 1 is satisfied, and C is a C category if 1 and 2 is satisfied. So C is a C category if 1 and 2 are satisfied for some K. Okay, I spent quite a lot of time already on this, much more than I expected. But let me already give you some examples. Let me skip to examples. So first, if you have any QCQS scheme, and even spectral scheme if you like, then we can consider the category of perfect complexes over X, and this is right. This is a C category. This is a C category. And the compactly generated weight structure in this case is given by, so if you take the incompletion of this, then this is category of quasi-coherent complexes over X. And in here, I can generate a weight structure by the class of perfect complexes that become weight co-connective on every affine scheme. So that, okay. So yeah, we apply the theorem with S being equal to perf X less or equal than 0. And this is by definition complexes of negative Tor amplitude. Let me formulate it this way. Of non-positive Tor amplitude. Right, okay. Another example is that, okay, assume we have an additive category, oh, sorry, an exact category. And it could be an infinity category. So there's a notion of an exact infinity category. Then in this case, there is a well-defined derived infinity category of E. And in here, I can consider the subcategory of complexes, sort of non-positively concentrated complexes. And again, I can embed this into int of GBE and can consider the weight structure generated by this negative class. So this is my S inside here. And now, so DBE is a C category. If so this gives a structure of a C category to DBE if E has finite cohomological dimension. So this means that the mapping spectra inside DBE between objects of E are going to be minus K connective for some K. Okay, maybe the addition to the first example that I forgot to say is that you can also, so example 1 also works for algebraic stacks, but you need to, at least up to now, we only figured it out under some additional assumptions. If you assume the following, that that the quasi-coherent complexes on X are is a compactly generated category, if O of X is compact, and furthermore, any connective object admits a map from a connective perfect complex. Okay.
What are examples of algebraic stacks satisfying these three properties?
Right. So for instance, in characteristic 0, you can take any quotient stack. So you take any affine group scheme, and it acts on any algebraic space. You take the quotient, it satisfies that. But it's also satisfied more generally. So there are, I don't have time to go into too much details about the conditions, but this has been thoroughly studied, and there are some positive results in this direction. Although it's not really clear what the right generality in the geometric setting really is. Like it's not really like there is no you know, a nice description of these subcategory of stacks satisfying these conditions. But for instance, any quotient stack.
Thank you.
Okay, and let me maybe tell you the last interesting example is that, okay, assume you have C, well, okay, assume you have int of C, stable presentable infinity category, which is also weakly approximable. Assume in the sense of Niemann. So the conditions, so if you try to remember what the definition of approximability is, it says that, okay, first of all, there exists an integer A and a generator, compact generator, that satisfies two conditions. So you have these subcategories that are generated in a range of objects generated in a range. And you want to say that, first of all, any object that is orthogonal, well, okay. How do I say this? Yeah, essentially you want to say the following, that for any x in int of C, there is an exact, well, yeah, there is an exact sequence of this form from here to x, and let's say, oh yeah, I forgot, oh, I see my confusion. I forgot to say that there is a T structure. Sorry about that. So, and there is a T structure. And okay, so now we say that G is bounded in this T structure. So G is bounded in the T structure, and in fact bounded below and above. Well, not quite, but bounded in the T structure from below. And orthogonal to high enough shifts of the T structure from the wrong direction. So map from G to int of C T greater or equal than A is connective. And the second condition is that for any object of your category, for any object in your category which is connective, there is an exact sequence which makes it, which sandwiches it between a one connective object and an object generated by G. So this is int C T greater or equal than 1. And now, if you think about this condition, the condition 1 implies, so now if you take your category int of C with a compactly generated weight structure, The positive part of a compactly generated wave structure is it also generates a T structure. And with this T structure, if you assume that this T structure is that T structure, then the conditions 1 and 2 correspond exactly to the condition 1 and 2 of a C category. So the first one tells you that the object is bounded in the weight structure. This is why there is a difference between these two subconditions. And the second condition tells you that you can approximate any object in the weight part by objects from this subcategory. And in particular, it's going to be all of the transition maps in such a presentation are going to factor for connective objects, because all of these objects are connective already. So anyway, what I want to say is that under these assumptions, C can be shown to be a C category. And C is a C category. I forgot to say that if you have a weakly approximable category, then it's also weakly approximable with respect to any equivalent T structure. And the T structure generated by this weighted formalism, by this compactly generated weight structure, positive part, is going to be equivalent to the standard one. Now let me formulate the main theorem. So let C be a C category. In this case, there exists a sequence of functors these are not fully faithful, I'm sorry. Such that each functor in the diagram is the composite of a localization functor and a fully faithful embedding. And it's a localization, and it's exact. So okay, this is f0, 1, fk minus 1. And so the following is satisfied. All CIs are bounded weighted categories. Each Fi, so for each Fi, sort of the kernel is equivalent to the image up to idempotent completion. And second, each functor is a composite of a localization and a fully faithful embedding. So localization and a fully faithful functor. Okay. So let me just say 2 sentences about the proof, and then I will say how it actually is used. So if you remember this description that I gave you, this equivalent description of 2, it already tells you the first step of the sequence. So we kind of want to say that this is our C1. And then this is, by definition, also a C category for a smaller level of level k minus 1. And so we can repeat this process until we reach level 0 or level minus 1, if you like, where you get the weight structure. So you sort of induct on this sequence. And now, okay, corollaries, which you can, well, okay. Let me also say that this sequence is actually functorial. So okay, remark. The sequence is functorial in weight exact functors. And moreover, you can show that if you have a functor C to D, which induces a weight exact functor ind of C to ind of D. So let me just say that it's weight exact. And we assume that on the heart of the weight structure, it's an nilpotent extension or K connective or any of the notions that you can come up with on an additive level. Well, but okay, if it's a nilpotent extension, at least nilpotent extension, then CK to DK are also nilpotent extensions. And so in particular, you can reduce, you can just generalize automatically any result that you know about nilpotent extensions of weighted categories to result about nilpotent extensions of C categories, just using this resolution. And so the first corollary that we have is that if you have C to D nilpotent extension of C categories, then the square K of C goes to K of D, goes to TC of C, TC of D is Cartesian. Right, and the proof is an immediate application of this sequence and the fact that all of these are localized and invariant, and so they send this kind of sequences to composition of fiber sequences following one after another. But then, in fact, all of these CIs except the last one will satisfy Lindbergh-Swindle, and so to prove anything for C. For localized invariance of C, it's enough to prove it for localized invariance of C of K, CK. And then, okay, another corollary, which is actually even simpler. So if you have C, which with the C category, which is a C category, and say it's a C category of level K, then THH or HH, if you like, if you work in the linear setting, is minus K connective. So this seems to be something that people did not quite realize. But it automatically implies that, so there was this question that I found in the paper of Kananako, Nima, and Stellati. They asked the following: assume you have any compactly generated category. So we have some ind of C. It has a generator G. And this generator is bounded in the weight structure in the sense of weakly approximable category. So we just have that G is in ind of C T greater or equal than minus N. sorry, minus a, and it's also orthogonal to end of c t greater or equal than a. So this is the first condition in the definition of weak approximability. So assume we're in a situation when this is satisfied. Then the question was, does it automatically imply that actually the second condition is satisfied, the condition that you have this fiber sequence sandwiching any connective object between one connective object and the object generated by G? And so if it were true, then in particular, any such category, we would have that THH of C would have to be minus k connective for some k. But we can find examples of a category satisfying this, where this condition is not true. So for instance, we can take a topological space X, and we can take the ring of cochains on X. This is, I mean, this is a ring spectrum, so we can take modules over this. And in this situation, if X was homologically bounded, then these two conditions are satisfied. So if X homologically bounded, then one is satisfied. But on the other hand, we know how to compute THH or AHH in this case by the theorem of Lode. So we know that THH of C star X is the same thing as C star of LX, where LX is the unpointed loops of X. And these, of course, can be highly non-connective, highly non-connective because, well, yeah. So if you have S2, then this is the loop space. This contains as a summand the loop space of S2, and this is huge. This has this is unbounded homologically. So so this already gives you some interesting examples. So I don't think I have more time. I could talk for another hour, I believe, but I don't think anyone would want that. So please let me know if I should stop here.
It's up to you, I guess.
Let me just okay. If you give me like 10 more minutes, I can give you yet another connection that I wanted to emphasize. Or maybe I'll try to make it in 5 minutes. Sorry. So there's been yet another notion defined by Victor Saunier, that of a hard structure. So. Hard categories. And originally, when formulating all of this theory, we thought that maybe this is the right context to actually do that. But eventually we realized that in the resolution theorem that I told you about, we need to consider weight exact functors and not. So, okay, a hard category is something that essentially extends the notion of a weight structure to not be equivalent to additive categories, but also to exact infinity categories. So we have CAD bounded weighted infinity, and this is, well, almost equivalent to additive categories. And then additive categories can be generalized to exact infinity categories. And so Victor found out the specific conditions that we need to impose on your category to ensure that it's equivalent to the derived category of an exact infinity category, bounded hard.
Pova, just let me interrupt.
Yes.
This is actually joined with Christoph Winges, like this equivalence. I only knew to do the fully faithfulness, and he helped me find out the other direction.
Yes, thank you. Yes. Yeah, I remember that up to idempotent completeness, it was like that. But then you with Christoph, you figured out how to what precisely the idempotent the conditional idempotence you need to impose so that it's in equivalence. But anyway, yeah. So I guess Christoph has defined. Victor has defined this notion, but this theorem is joined with Christoph. Yes. And anyway, so what I wanted to say is that in this setting, it's any bounded hard category. But let me put this arrow in quotation marks, gives rise to a C category. Well, okay, up to, but so at least it always gives rise to a compactly generated weighted category. And if you restrict to those hard categories that have bounded cohomological dimension, then this maps into C categories. But the problem here is that this is not quite functorial. Like we have a C structure whenever we have a hard structure of bounded cohomological dimension. But the functors are a bit different. Nevertheless, somehow in the whole process of the proof, it turns out to be useful because it's not entirely clear in the resolution. Where was it? Yeah, here is it. Yeah, it's not entirely clear that this category is weighted category if we start from a C category of level 1 or level 0. But because of this formalism of hard structures, we actually know that this is more than just a C category. This always comes from a hard structure. Yeah, I guess I've probably confused quite a lot of the audience, but let me just say that this is yet another notion that is useful in this context. And let me stop here.
Thank you, Baba. Let's all unmute ourselves and give the speaker a round of applause now.
Thank you.
If you have any questions, please ask them now.
So I like these resolutions very much. So I have some questions, maybe 2 questions related to them. So the question is whether it makes sense to compute them explicitly, maybe for this geometric example. And the second question, yes, so if you suppose you have an exact sequence that satisfies these conditions, does it correspond to a C structure, and can you describe, maybe recover this C structure if you only have all the rest of this sequence?
So you mean if you already have such a sequence, so the opposite direction of the theorem, if you have such a sequence where everything is away, yes, this is true.
Oh,
then you have a C, then you have a C structure. As for your first question, so I mean, this resolution business started from, like, if you want to generalize something from connective ring spectra to additive categories, you're essentially doing the same procedure. Let me quickly say it. Like you you start from some bounded weighted category C, and then you can take the category of modules over the endomorphism ring of the sum of all the generators, so all objects of the hard, say. And then this is going to be a fully faithful weighted embedding, and the quotient is again going to be perfect complexes over some ring spectrum, over some connective ring spectrum. And this is essentially the 0th step of this resolution. This is essentially how it looks if you were to start from a C category of level 0. And I mean, I don't know, it's sort of explicit, but it's also highly not commutative, highly not geometric. It's some version of the Kalkin algebras. It's some metric string modulo the ideal of matrices of finite rank. And in theory, it's some higher categorical analog of that, I would say. So I don't think
maybe a third question, is there any hope to obtain some smaller resolution?
Yeah, I mean, so you have this level K in the definition of a C category. You cannot obtain a resolution. So assume you pick the minimal such K, minimal level, then you cannot obtain a resolution that is shorter than K. But it's somehow, if you're looking at the C category, it's sometimes not clear whether you can actually make it shorter. It's not entirely obvious. So I mean, it's hard to find this minimal level sometimes.
Thank you, Mikhail. Any other questions? I had just a curiosity about the question that it's basically an addendum to the stacks question that I asked during your talk. So those algebraic stacks, are they, I don't know, QC with affine diagonals? I mean, I'm trying to understand if your class of stacks are like a subclass inside Aleph-0 crisps.
Yeah, so if you have
like every close point must have positive characteristic. That's the other requirement, I think.
Yeah. So you right. I mean, so there are two conditions. So I mean, okay, three conditions. So first condition is that the diagonal, you want the diagonals to be somewhat nice. I mean, affine diagonal is currently how it's written in my draft, in our draft. But I think affine diagonal is actually not necessary per se for the constructions. So the generality that I expect is that you have QCQS algebraic stacks with separated diagonal. Oh, sorry, not separated, quasi-affine diagonal, quasi-affine diagonal. What am I saying?
Mm-hmm.
Quasi-affine diagonal. So in particular, any QCQS algebraic space satisfies that. And then there are two conditions. So one is essentially equivalent, or like it's some version of crispness, like Aleph-0 crispness. So compact generation of QCO. But then the other condition is somewhat subtle. It follows in many cases where you do no crispness. Like if you have a cover, if you have a map like this étale cover by stack satisfying resolution property of your scheme, then of your stack, then your stack does satisfy that. But in general, it's not the condition that I saw in any of the stacky papers of QCO positive. But yeah, I thank you for your question. I forgot to add that so this resolution result in particular applies to stacks. And in particular, we didn't know DGM theorem for stacks that say don't satisfy the local structure theorem. But now we do. Now we know that for any in characteristic zero, at least for any affine quotient, it does. And this is this is much better than it used to be.
Thanks. And congrats on finally settling the question about the superfluousness of the second Wick approximability axiom. I'd heard Amnon mention it in countless talks, that this is a curious thing, this is a mysterious question.
Who should I attribute the question to? Amnon or
I think
the three of them?
morally Amnon, but maybe it appears in writing in the CNS paper, as you correctly said.
I see.
I don't know, when Kabir, if he is still here, maybe he can correct me, but I think.
No, yeah, I'm not, I mean, has definitely had asked this before also.
Yeah, in writing, I think that's the only
Yeah,
place
but the
where
CNS paper is perhaps the Karanakuni Stellari paper is, yeah, first one, where it appears. Yeah.
Thanks.
Yeah, and when you were stating that example, the weak approximability thing, you said weak approximable, and then you said presentable separately. But if it is weak approximable, there is a single compact generator, so I have presentability.
Yeah, I mean, I just wanted to say that it's, wow, where was it? I guess.
It's okay, yeah.
I mean, you could say that it's, I just wanted to say that it's end of something, I guess.
Yeah.
So, just because I wanted to talk about C itself, you know.
Any other questions? Yeah, sorry. Any other questions, anyone? Questions or comments?
Okay, I have some elementary question.
Yes.
So is it true that if you have some nilpotent extensions, yes, between two infinite additive category, for example, between perfect complexes, is it true that you can find some schemes, yes, and nilpotent extensions such that such that perfect complexes is for the scheme is equivalent to your initial additive categories?
I mean, not any additive category is.
So there is some theorem, I think, due to Niemann or Sanders, maybe. Yes, if you have some finite morphisms between triangulated categories, yes, then you can find morphisms of schemes, yes, and tensor triangulated equivalents, yes.
I see. So you're saying that you start from one category coming from geometry and you have a nilpotent extension of that.
Yeah. So yes, if I remember correctly, so if you have some finite morphisms between derived category of quasi-covariance, yes, scheme to some tensor triangulated category, then you can find geometric morphisms, yes, between morphisms between schemes, which induce this triangulated map. Is it true for nilpotent extensions?
I mean, this sounds plausible because any nilpotent extension, it's monadic, so at least your modules over some ring spectrum. But then the problem is this ring spectrum might not be commutative. Yeah, I'm not sure. I'm not sure about that. Yeah, I'm not sure.
Okay, so thanks.
Thank you, David. Any other questions or comments? Anyone? If not, let's thank the speaker once again.
Thank you for the invitation.
Can you stay on for 2 seconds? I want to ask you a logistical question for April.
Oh, sorry, what?
Can you stay on for 2 seconds after this talk?
Yes, I can. Yeah.
Okay, thank you all for coming. Hopefully, I'll see you next week. Bye-bye.